Hello all, welcome back to this series on static timing analysis. So in this video, we will derive the equations for setup time and hold time. Setup time as well as hold time by considering two parameters with skew. Skew can be of two types. One is positive skew as well as negative, and without skew as well as without skew. So in our previous session, we have theoretically discussed this concept, the concepts of setup time and hold time and setup time and hold time violations. Now let us derive the equations for this by considering the following things: without skew and with skew, that is positive skew and negative skew. Okay. So first let us consider the circuit which we are going to deal with. So the previous session circuit only I am going to take, that is our 2D flip-flops connected like this. This is the flip-flop one. Outputs are Q and Q bar. D, Q, Q bar. These are my inputs. And here there is a combinational circuit connected here. And this is connected to second flip-flop input. And this is my clock pin. So like this, these are both synchronous circuits. So the same clock is given to both the flip-flops, right? So our first case is there is no skew. No skew. There is no difference in the frequency or time period between of the two flip-flops. That is, the same clock is given to both the flip-flops. So I will draw it diagrammatically. So the waveform for the two flip-flops. So this is the clock which is given to flip-flop 1 and flip-flop 2, right? So this is for flip-flop 1, and this is the positive edge where the two flip-flops will working on. This is a clock for flip-flop 2. So this clock is given for flip-flop 2. So at the positive edges, the two flip-flops will be working. And the same positive edge, the flip-flops will be working, and there is no skew. Okay. So the flip-flop 1 will sample the data, let's say at point 1 at this edge. So while considering the setup time also, so let's say this is the setup time of flip-flop 1. This is T setup, and let's indicate the hold time of the flip-flop 1 by T hold. So let's say this is the hold time of flip-flop 1, T hold. Okay. Now for flip-flop 2, let's say the flip-flop 2 will sample at this clock edge. So let's say this is point 1 and this is point 2 and this is point 3. So let's say the flip-flop 2 will sample the data at edge or point 3. So before the setup time, the data should be available. So this is the T setup. Let's represent this as T setup. And the whole time of flip-flop 2 is this. So this interval is the whole time of flip-flop 2. T hold. Right? So let's say this point is point 4. Okay. So for flip-flop 1, the data should be available before the setup time, and it should be maintained throughout this whole time. Okay. And for flip-flop 2, the data should be available before the setup time. That is, at this point, at point 3, the data should be available and it should be maintained through this whole time also. At point up to point 4 minimum, it should be maintained. So I will write the conditions here. So for flip-flop 1, the data should be applied before the setup time, and it should be constant for minimum amount of time. Minimum amount of time interval, that is hold time, that is hold time. So during this time interval, the data should be constant, minimum amount of time. It can be constant after this also, but it should be minimum amount of time, it should be constant. And this data from the flip-flop 1 is propagated through this combinational circuit, which has some propagation delay, which has some propagation delay. Let's say the propagation delay is TPD, okay, which through this propagation delay and it reaches to flip-flop 2. So when it should reach, so it should reach the flip-flop 2 data pin before the setup time, okay. So at somewhere here it should reach, or here, okay. So it should reach before this setup time interval, so that there will be no setup time violation. So for flip-flop 2 I will write the conditions. So for flip-flop 2, the data should reach before the setup time interval from flip-flop 1. Where the data is coming from? From flip-flop 1 through the combinational circuit. Through the combinational circuit, which has some propagation delay. Okay. So now let us calculate the setup time. Let us derive the equation for setup time. Setup time with no skew. Since the same clock is given, so there is no skew. Let us consider this, right? So, what is the arrival time when we are getting the data to the second flip flop? That is given by the arrival time. That is called the arrival time. What is this arrival time? The time at which the data is reaching to flip flop 2 from flip flop 1 is called arrival time. So, the time the data reaching to flip flop 2, reaching to flip flop 2 from flip flop 1 via combinational circuit. This time interval is called arrival time. So how to calculate this arrival time? Simple. So what is the propagation? What is the clock to Q delay for flip flop one? So flip flop one has some clock to Q delay, right? So that is represented by T clock to Q. The time interval the data takes to get the output. So the time the flip flop takes to produce the output is called clock to Q delay. So what is this T clock to Q delay? The time the flip flop takes to produce an output, to generate an output after giving the input to the flip flop, right? So the what is the arrival time here? So it is nothing but T clock to Q, that is the delay we are facing, the time we are taking for the data to coming out from the flip flop one, plus it is going through combinational circuit. So we will consider the combinational circuit delay also, that is T combinational, right? So this is the arrival time. So after this delay, we will get our data to flip flop to arrival time at flip flop to data pin, right? So the data is reaching after T com plus T clock to Q delay. After that delay, after that time interval, we are getting to this second flip flop. Next, what is the required time? So next we'll see the required time. What is our required time? What is the requirement here? We should get the data in this time interval or before this time interval, that is before this setup time, right? So how to calculate this time, which is given by, so the total time period of this clock is, let's say, T clock, okay. The total time period of this clock is T clock, okay. So how to get this point? Just subtract this T setup. So up to here, if you want a time period, we'll subtract by T setup. So T clock minus T setup. So we will get the time interval before this at this point. Okay, so the data should be present at this point. Okay, so the maximum time the data can be given to this flip flop 2 is t clock minus t setup. That is a requirement. So what is the required time? T clock minus t setup. This is the required time, right? So to avoid any metastability, that is to avoid setup time violation, to avoid metastability. So if there is a setup time violation, there will be metastability, right? To avoid metastability or setup time violation, what we'll do? What we should do? Our arrival time, okay, the data when we are getting the time should be should be less than the required time, right? So if it is greater, then we will get the setup time violation. So this arrival time should be less than this required time. If it is greater than our required time, then it will cross this condition and it will give a setup time violation, right? So the arrival time should be less than the required time. So this is the requirement we have. So to avoid metastability or setup violation, our arrival time should be less than the required time. So what is the arrival time here? It is given by t clock to q plus t combinational, which should be less than or it can be equal to t clock minus t setup. So it can be written as t clock to q plus t combinational plus t setup, which is less than or equal to t clock. So this is the requirement. This is the setup time equation. I'll write it here. So the t clock to q plus t combinational plus t setup should be less than or equal to t clock, time period of the clock. So this is the equation of setup time. Now let's substitute some random values in this and let's see what happens. So let's say our t clock to q is around let's say 1.5 nanoseconds, and t combinational is around let's say 1 nanosecond, and t setup, let's say it is 2 nanosecond, and let's say the time period of this clock is uh, 5 nanoseconds, right? So if we substitute the values, what we'll get? T clock to q is 1.5 nanoseconds plus t combinational is 1 nanosecond plus t setup time is 2 nanoseconds, which should be less than or equal to 5 nanoseconds. So 1.5 plus 1 is 2.5 plus 2 is 4.5 nanoseconds, which is less than or equal to 5 nanoseconds. This condition is valid, so there is no setup time violation, right? So what if the combinational delay is increased? What if the combinational delay is increased? Then what happens? Let's say t combinational is around 2 nanoseconds. Then what happens? Then 1.5 nanoseconds plus 2 nanoseconds plus 2 nanoseconds, which should be less than or equal to 5 nanoseconds. Then what happens? 4 plus 1, 5.5 nanoseconds, which is less than or equal to 5 nanoseconds, which is not valid. Then what happens? There will be setup time violation, right? So when the delay increases, like combinational delay increases, there will be, in this case, there will be a setup time violation. So this is how we calculate whether there is a setup time violation or not, by using this following equation. Okay, this is about setup time and setup time violations. Next, let's calculate hold time. Let's derive the equation for hold time. Now, what is the arrival time? Arrival time is same. The data is coming at the same time. Since we are not changing any delay for the whole time, arrival time is same. What is the arrival time? Which is nothing but t clock to q plus t combinational. This is the arrival time, right? And what is the required time here? What is the requirement for us? That the data should not change during this whole time, right? What is here? What is the required time? The data should not change during this whole time. Here also, so for flip-flop 2, the data which is given to the flip-flop 2 should not change during this interval, whole time interval. Okay, so the data which is given to this flip-flop 2 should not change during this whole time, right? So this is the requirement. So the data which is given to this flip-flop 2 should not change during this whole time. So we'll write it here. The requirement is t hold. So during this time interval, t hold interval, minimum interval, the data should not change. So the minimum interval t hold, the data should not change. This is a requirement. Minimum amount of t hold, data should not change. Okay. So the data which is given to the flip-flop 2, that data should be constant during this t hold time period, right? Now, so how to, so to avoid hold time violation, what is the requirement we have? The data which is given to the second flip-flop should be constant during this t-hold time period. So we will open that waveform again. So the data which is given to this t-hold should be constant during this hold time, right? So when we are getting the data, here we are getting the data, right? During this arrival time, when we are getting the data, what is the arrival time? T clock plus t clock to q plus t combinational, right? When we are getting the data, when we are getting, what is the arrival time? T clock to q plus t combinational. After this time unit only we are getting the data, right? Let's say somewhere here we are getting the data, and when we should get it, when we should get the data again, after this t hold, after passing this minimum time interval t hold only, we can get the new data. Okay, that is, the arrival time should be greater than the required time, right? So to avoid the hold time violation, the arrival time should be greater than the required time, or greater than, or no, it should be greater. Okay. Next, what is the arrival time? It is t clock to q plus t combinational should be greater than, what is the required time? T hold. Okay. So this is the equation for hold time. So the t hold should be greater than or equal to the t clock to q plus t combinational. So let's say, suppose, let us again substitute some random values in the place of t clock to q and t combinational, and let's check. So let's say if t clock to q is around 5 nanoseconds, and let's say t combinational is around 2 nanoseconds. Let us say this is 1.5 nanoseconds and 2 nanoseconds, and the t hold is zero point 0.5 nanoseconds, right? So if we substitute the values, then what we will get? 1.5 nanoseconds plus 2 nanoseconds, which should be greater than or equal to 0.5 nanoseconds. This is valid. So there is no hold time violation. And what if the t clock to q is 1.5 nanoseconds and t combinational is 0.5 nanoseconds? And let's say the t hold here is some 2.5, right? So what happens? 1.5 plus 0.5 should be greater than or equal to 2.5. So it is nothing but 2 nanoseconds. Not valid, right? So there will be hold time violation. Okay. So while designing any circuit, we should be keeping the delays in mind, and we should be designing accordingly to avoid the hold time and setup time violations, right? So if the delay increases only, there will be no hold time violation, right? So if the combinational delay of this particular circuit is increased, then the hold time violation will not occur, but there may be chances of setup time violation. And if the whole time if the combinational circuit delay is so far decreased, then there may be a chance of hold time violation, right? So these all parameters and conditions should be kept in mind, and we will be designing our circuits, right? So this is about setup time violation and hold time violation without considering any type of skew. Okay. So that's all for this session. Thank you.